We will now look at the integration of terms involving fractions of polynomials and also the square root of quadratic expressions in the denominator. There are a few techniques which we can use as appropriately. They are using standard forms as we have learned earlier, and therefore I will not be going through this technique in this video. Formula from the formula booklet, partial fractions, and we are also required to know how to use a combination of these three techniques to solve the integrals. In the formula booklet, there are several formulas that are given for integration. Of particular interest to us now are these four. If we see that a particular integral can be written in one of these forms or similar forms, then we can apply these formulas directly. For example, in example A, okay, we see that the term is 1 over x squared minus 4, which is exactly the same as 1 over x squared minus a squared, where a is equals to 2. Therefore, we can apply this formula directly to give us 1 over 2 times 2 ln of modulus of x minus 2 over x plus 2 plus c, which we can then simplify into 1/4 ln mod of x minus 2 over x plus 2 plus c. Now this is a simple example, and sometimes we may get a quadratic expression at the denominator which is not exactly the same form as one of the formula over here. But that does not mean that we cannot use the formulas. What we have to do is to simply complete the square to get 1 over x plus 1 square plus 2 dx. And now we can compare this term with this formula over here and see that we can replace x with x plus 1 and a square with 2. And with this substitution, we will be able to solve the integral very easily to get 1 over square root 2 tangent inverse x over square root 2 plus c. However, do note that although the x term can be changed into x plus something or x minus something, the coefficient of x must strictly be 1 if you want to make use of this formula. If the coefficient of x is not 1, like for example in example C, what we can do is to simply factorize out the coefficient of the x square to get 1/4 1 over x square plus 3/4 dx, which is exactly of the same form as the first formula over here, where a square is 3/4, and therefore we can integrate this very easily to get 1/4 times 1 over a, which is square root of 3 over 2 tangent inverse x over square root 3 over 2 plus c, which we can then simplify into 1 over 2 square root 3 tangent inverse 2x over square root 3 plus c. And we can do the exact same thing for example D as well. We note that this is of a very similar form with the second equation on top. And of course, we want to write it in the form of a squared minus x squared, where the coefficient of x squared is a 1. So what we have to do is to take out the 9. Note that if we take out the 9, there is a square root, and therefore it becomes a 3 instead of a 9 when you bring it out. So we get 1/3 times integration of of 1 over square root 1 over 9 minus x squared dx, which is exactly of the same form as our formula, where a squared is 1 over 9, and therefore we can get the answer to be 1 over 3 sine inverse x over 1 over 3 plus c, which we can simplify to be 1 over 3 sine inverse 3x plus c. In some cases, we can perform partial fractions to integrate rational functions. Take for example part A, which is exactly the same as example 1a. It can be solved alternatively using partial fractions instead of the formula that is given earlier. I will not go through the basics of performing the partial fractions over here, but you should know that these partial fractions in part A can be written as negative 1 over 4 over x plus 2 plus 1 over 4 over x minus 2 dx, which we can integrate very easily to be negative 1 quarter ln x plus 2 plus 1 quarter ln x minus 2 plus c, which we can combine into 1 quarter ln x minus 2 over x plus 2 plus c, and recognize that this answer is exactly the same as in example 1a. In example 2b, we can do the exact same thing by changing this into its partial fraction, 1 over 6 over x minus 5 minus 1 over 6 over x plus 1. And we can therefore integrate this to become 1 over 6 ln x minus 5 minus 1 over 6 ln x plus 1 plus c, which we can simplify into 1 over 6 ln x minus 5 over x plus 1 plus c. Lastly, in this example, I will show you how to split the terms up accordingly to make use of the appropriate techniques to solve for the integrations. In part A, we note that the denominator is already expressed as the simplest term, and therefore we cannot perform any partial fractions on it. Next, if we recall our standard form formula, which is of the form f prime x over fx, if our denominator is fx, then our numerator should be a 2x. We have a 2x on top, but there is an extra plus 1 at the back. But there is no worries, because we know that integration of 1 over x squared plus 1 gives us tangent inverse x. Therefore, what we can do is to simply split this integral into 2x over x squared plus 1 over x squared plus 1 dx. In this first term over here, we are going to integrate using standard form of f prime x over fx. And this second term can be integrated using tangent inverse x, which is found in the formula for your MF26. And therefore, we will get the answer of ln x squared plus 1 plus tangent inverse x plus c. Now in example B, we have a much bigger rational function, but the method to solve this integration is still the same. Let's first perform a partial fractions to split this term up into integration of x plus 2 over x squared plus 1 plus 1 over x minus 1 dx. Now, for this first term, we can apply the same technique as in part A to split them up into two terms. And we will end up with x over x squared plus 1 plus 2 over x squared plus 1 plus 1 over x minus 1 dx. For this first term, we need a 2 in the numerator so that we get a 2x, but it is just an x now, so what we can do is to multiply by a 2 and a half outside to balance the extra 2 given. And with this, we can integrate it to be half ln x squared plus 1 plus 2 tangent inverse x plus ln of x minus 1 plus c, and that's it.